This second paper is entitled Smoke Management. In a car park. And it's an application of using CFD to calculate the smoke behavior in underground car parks under different conditions. It's co-authored by Dalia, Khalil, and myself. So I'll be giving a brief about the introduction of the system, the different equations we're going to solve, literature review, methodology, case studies, and I'll put some animation. Most of the internationally known codes, as well as the Egyptian code, I'm sorry, it's in Arabic here, NFPA 88A, regulates the calculations of closed parking areas with automatic sprinklers. So in this case, we know that from the statistics of fires and casualties in underground car parks that we have very devastating accidents in case it's not sprinkled. And a sprinkler is a small gadget that sprays water in case of fire. Before we used to have ducts to extract the smoke, and nowadays we use jet fans, you can see them in here, to replace the ducts. Why? Because when you have ducts in a parking, the ducts may overlap with your other services like water pipes, cable trays, and things like that. And with the advancement now, we have seen an example today about a building with 4 floors of car parks underneath. Then the designer would like to reduce the ceiling level of these underground basement or car parks in order to have more rooms. So we have to set a level, a minimum level that car parks should have. Then we talk about the spray of water to overcome the fires, and this has to be put in certain positions. So the objective is to demonstrate the physical effect of the sprinklers, and we model here not only the air, but also the water spray droplets as well. So here, this is a quick review of the papers published on the matter, and it's all related to calculate and predict, measure carbon monoxide distribution, pressure difference effects, velocities and temperatures in this. In order to use a computational or a mathematical model, it's better to be able to assess its validity by comparing the results into a well-known experimentation. And in this case, we took the experimentation of Ho, where he's specifying the location of the measuring points, and then we compare the measurements and the predictions together. Like here, this is one of the cases of the validation. So you have the experiments and you have the predictions in terms of temperatures. And then the base case study we're going to simulate this afternoon is a parking area. And for parking area, you have a minimum by code. We have the minimum areas for the cars and also for the routing, the alleyways. Of course, the designer would like to reduce as possible the public areas. So we have to be very careful when applying this. I'll show you here an example of what happens in a car park. So you have the jet fans. With the jet fans, they prevent the smoke from going down. So I can escape. If I'm here and the smoke naturally, it comes down, and until it goes down and down, until it is 80 centimeters from the floor, it is called inferno. Nobody escapes. So with the jet fan, it keeps the smoke at a higher level. So it does not affect you. You can run, you can exit. And also the fire brigade people can come to put off the fire. Here you can see the cars are parked and it's running with time. Now let me go to the next one. Now we advance, we put curtains. You can see the curtain. So the curtain limits the smoke. All this is simulated using equations. Which equation? Governing equation. Mass, 3 momentum equations, energy equation, species concentration in a grid that maps the domain. And we talk here about, say, 100,000 grid nodes or more. It depends on the situation. I just wanted to show you that this is what we look for. Which design option we use in order to safeguard the space. So of course here we have different grid sizes. Here we have 80,000 and it's divided into 16 meshes. And in this case we have jet fans. The jet fans are the small dashes and these jet fans, like, they transfer the air or the smoke from one place to another, like a virtual duct. So you have a jet fan and another one. The first one takes the air, the smoke and move it into the second one and so on. We use, of course, in the code, we have different air change rates. In case of fire, it's 10. In case of normal, it is 6. And it depends on the code, of course. Of course, also we have sprinklers. Sprinklers are water spray to put off the fire. And these are working on pressures of about 1 bar till 6 bar. We're going to investigate that as well. Grid sensitivity is very important because you will get results anyway. So it's better to get results with a grid that the results are not grid independent. So your solution will be sound. In this case, we tried 3 different grid sizes, and you can have 11 million, simulation 1. Simulation 2 is 1.5 million. Simulation 3, which is a coarse one, is about 180,000 grid nodes. So these are the effects of grid sensitivity, because in every mathematical formulation, we have to do at least 2 exercises. First, assessment of the validity, and then we have grid and grid sensitivity. That's the solution does not depend on the grid, and also that the equations are converged, because in this case they are by trial and error. You assume a value, then you correct, and the residuals should go to about 10 to the power minus 6. These are the simulated case. In each case, as you can see, this is a horizontal plan. So in each of them, there are at different time steps, 180, 240, 300, and so on. And you can see this is a visibility. What is the visibility? That's the distance you can see along. So the fire brigade people would like to have a visibility of 30 meters. If it is less, then there will be a problem. And you can see here, you have the fire this is the fire location, and you can see that the visibility changes. And here, for example, all this at 1.8 meter, and this is the visibility contour, again, at different conditions. So when we have design options, what to do? If we use sprinklers, what will be the results? So here we have in the geometry, we have the fire occurring here, and these are 6 deluge. Deluge is you divide the system into different zones, where one zone starts to react if the fire is in this zone. So in order not to waste the water to be sprayed. And these are some examples of the visibility along the park. I'll skip this quickly for the sake of time. But also we consider 3 different options. 3 meters clear height, 3.6 meters height or 4 meter height. Of course, the 4 meter height will be better, but of course the stakeholders, the owners, the client will refuse this because it means that the limit of the building height will change, and that's not good for him from the commercial point of view. So here, for example, we see the visibility at different heights using sprinklers. Why? Because I don't want the sprinklers to stop the effect of smoke evacuation, as one would expect. The ducted system, here this is a case of ducted system, where we have also typical duct at certain levels. This is ducted, and you can see that the reddish color is still there. If we use jet fans, different cases with increasing the sprinkler pressure, then the higher the pressure, the better. You can see here, this is at spray water at 1 bar, here at 4 bar, and there at 6 bar. Why I'm saying better? Because this is a fire source here at the arrow, and the rest of the space is still clear. You can see. Now let me show you here. I hope it works. Okay. This was to be a movie showing the sprinkler water. It is showing this. But it takes time. Different computers, different speeds. So first you have the smoke. Supposedly people will escape. Then the water spray comes down, and to predict the spray, you have to look to the drop size, and you use the Sima-Tanasawa distribution for the D32 for the particles, and so on. We thought at the end of the paper to try different heat release curve, and to see that this is how the heat release increases and then it cuts down. And we tried this in different cases. So here you can see at the first one, where the first sprinkler start operation after 103 seconds, and so on. Now I'll show you a movie. Yeah. That's about evacuation. After we calculate the smoke management in the space, we see how many people can be able to escape. I do that when we are doing modeling a metro station, a mosque or a church, just to check how many seconds people will need to evacuate. I did this for the Grand Mosque in Mecca, and I did it for churches also in the Middle East. So here for one of the buildings, that's the time. You can see the time on the top is showing how many people already managed to escape. We did the calculations for designs that are made by others just to check how many would be the casualties. It's a bad thing to see that you expect that 2 or 3 will not make it. But I'm trying here to show the value of computational techniques. We just solve equations that are known, very well known, with some assumptions in order to be able to predict the behavior in environments that we live in and we use. In conclusion, that we did model spaces, car parks. We modeled the physical effect of the sprinklers at different pressures and also at different heights in order to be able to guide the designers for a better and more safe configuration. Thank you very much.